Okay, welcome everyone to my talk on everything you never wanted to know about Java class initialization. I'm Christian Wimmer. In my day job, I'm the architect of GraalVM native image. But that's more a side topic of today because in the last years working on GraalVM native image, I actually spent way too much of my time kind of dealing with class initialization issues. And so I thought it's a good idea to kind of summarize what's going on the class initialization side. So we will go through the basics. What is a class initializer? How is it behaving? But then the main point is like, well, why am I here? Why am I talking about it? Why is all of that suddenly a problem after having class initializers for many decades now in Java? And then I'll show some real-world data. It's like what is a Spring application actually doing in terms of class initialization? There's a little bit of a wild and crazy ideas session at the end, but in the end, it's like I want to raise awareness that there is a problem, and I'm not really presenting a solution for the problem. That is kind of for us to, I think, fix in the future. So what can you do in a class initializer? The simple answer to that is everything. Because a class initializer is just a method with the special name CLInit in these funny brackets. And Java-C creates it, and the JVM executes it before the first time a class is used. Every class can have a class initializer, and unfortunately, everything, including interfaces, enum records. The only good news is arrays don't have a class initializer, so it's like I don't need to mention arrays for the rest of this talk. Class initializer executed exactly once before the first usage of a class, and there's all the synchronization done by the JVM for that. That's very convenient, but can also cause problems because it's like, well, you have implicit synchronization, and as soon as you have synchronization, you can have deadlocks. And it's fine-grained, so every class has a separate monitor. There are lots of good usages, so I'm not saying that class initializers are per se a bad thing and need to die in a fire. There's like you can initialize your immutable static state, and it's guaranteed to run only once. It's like very easy to use, very good. But there are lots of problematic usages, and that's the thing, of course, I want to focus on. There's capturing of immutable state, where I put immutable in in the funny way, because like, well, you think it's immutable, but it's not immutable, and the canonical example for that is processor count. And then there are lots of very bad usages, like cyclic dependencies, exceptions in the class initializer. So what's the thing with the processor count? It's like, you look at CLInit's class initializers. For example, you don't need to look far in the JDK in a Java util concurrent package, and there's a class exchanger, and it has a static final field, nCPU. It catches the number of available processors. It's good to have that in a static final field. And of course, if you do it once, well, you can do it 3 times, and you have 3 static final fields caching the available processor count. But of course, the processor count is in no way immutable. So it's like, basically capturing the processor count 3 times, and you can have 3 classes in the same package who have completely different processor counts. And especially when you resize your container, and it's kind of, you start with a small container with 1 core, then you realize, my application needs more CPUs. You resize your container to 32 cores, and all your concurrent code still thinks I am running on a single core, so I don't need to optimize anything for concurrence. It's like once you put this not really immutable external state in a static final field, there's no way you can ever recover from that and change that. So external state can change at any time, but it's captured at a pretty random time, and I will come back to this random time more in the remainder of my talk. But first, let's talk about cycles in dependencies. Since every class initializer has a separate monitor, there needs to be a mechanism. Well, if you have recursive invocations, if a class initializer initializes another class, and then this class goes back to your first class A, then it's like, well, you have a cycle, and locks are reentrant, and it's like, well, you just ignore the reentrant invocation. But in this reentrant run of the class initializer, well, you haven't initialized your class yet. So it's like all the static fields are still 0 or null. And that's, of course, the source of many Java puzzlers. So it's like has been around forever. I don't need to go into details there. But the problem that I think is overlooked in general is that as soon as you have multiple threads involved, you can also get deadlocks because you have fine-grained locking. And as soon as you have more than one lock and more than one thread, you can deadlock. And the real problem is, as soon as you deadlock in class initializers, there's no way you can recover from that. There's no way to interrupt these locks. There's no way to kind of use this class anymore. The only thing is you can do a hard kill of your JVM, and that's the only way you get out. You cannot even do a system exit, because like system exit will wait until your class initializer has completed, which it will not. So it is every cycle is a potential deadlock. Is that a problem? It's like, well, I have the kind of simplest possible thing of a cycle between class initializers, two classes A and B. Can this application deadlock? I start two threads. I have two classes that are initialized. So according to my definition, yes, it can deadlock. And we can actually simulate that pretty efficiently. We just need to help the OS a little bit and make the OS thread suspension a little bit more predictable. And so it's like, yeah, in case it happens that both class initializers get suspended by the OS at the beginning, then this application is a guaranteed deadlock. So just by adding these two thread.sleeps, I have a kind of guaranteed deadlock. And it's like, yeah, but is that really a problem in reality? Well, I know of one bug because I filed it in the core JDK class. It was a cyclic dependency in the Java lang constant package of the JDK. And when we had native image and we did class initialization in multiple threads in a little different order than usually in the JDK, and it deadlocked. Of course, completely transiently in one of every 1,000 runs of a native image build. But in the end, in that case, it was an easy fix because it's like, well, you just break your cycle. So yes, I would argue cycles are a problem and deadlocks do exist. It's just that in most cases, it's because, yeah, you don't have enough threads yet, and it's like the timing is right, so you don't really notice that. But keep in mind, with Project Loom, we just added orders of magnitudes more threads. So it's like, things are definitely not getting better. Now, to shift gears a little bit, when is a class initializer executed? Well, there is this nice specification in the JVM specification, section 5.5. And it has this bullet points. A class is initialized, and the most important bullet point is the first one, just before the first usage of the class. And then down at the bullet point here, it's like, of course, you need to initialize a class before you initialize any of the subclass. So it's like the superclass is always initialized before. And there's this nice point here that's like, well, not the clearest language, but it basically says, well, if you have an interface with default methods, then you need to initialize that interface before you can use any class that implements this interface. That's also very interesting, because it's like you have an application, and in my case has a record, and the record implements an interface. The interface does not have a default method, which means I can perfectly use this record without needing to initialize the interface I. So it's like I can throw an exception in the initializer, and all is good. By the way, funny side note, it's like interfaces are the kind of only class construct in Java where you actually cannot have a static block directly, but you can have a static final field that has an init method, and that way you can also get a class initializer. So just the fact that there is no static block in an interface does not mean that there cannot be a class initialization there. And so it's like now I make a little change in my interface, I add a default method, and suddenly the interface is initialized when I use the record R. Which is also, I think, the very overlooked fact that adding a default method to an interface is really a breaking change regarding class initialization behavior. So you need to be very careful when you add a default method and when you want to preserve compatibility, because the first default method that gets added can really screw up your class initialization story. And then there's this nice third point hidden there in the middle of the specification. Well, a class is initialized in certain other kinds, which basically means in reality, a class is initialized before the first usage or whenever the JDK or JVM wants. And I have a few examples for that. My favorite hello world in Java is like, I have a main method that does nothing more than looking up the annotation of the class. And everyone who is familiar with annotation knows it's like, well, a class can neither have the override annotation, nor is the override annotation even preserved in class files. So it's like, it's clear that kind of this main method does nothing. But this class has another annotation. The annotation uses an enum value. The enum implements an interface. The interface has a default method. And so, unfortunately, any annotation operation in Java, even if it's just is annotation present, materializes all annotations that are on the element, which means when I run this application, I actually get my init method executed, and I'm printing the stack trace there so that we see it. It's like, yeah, I'm in my hello annotation.main method. I'm in is annotation present, then there are lots of internal frames of the JDK. In the end, it looks up the enum value, and the enum value lookup, of course, needs to make sure that the interface is initialized. You see here, I was hiding a lot of stack frames here, because in reality, that is a pretty deep stack frame here, which also is then relevant in later points, because it's like, well, you really have a really deep stack in the initialization. And I said, if there is any kind of exception in the class initializer, you can, the class initializer kind of fails, and the class kind of goes into the initialization failed state, and you cannot use that class anymore. So that means if you get a stack overflow error, because, well, the JDK decides to initialize this class at a bad point and does it in a very deep stack, then it's like suddenly all of these classes and annotations and interfaces, everything involved here is kind of unusable. And again, I need to kill my VM to recover from that. Then there are, of course, bugs triggering class initialization in the JDK. One thing we found is like, well, there's this nice thing, find static var handle. It's like, well, you want to look up a var handle for a static field, and you read the specification of find static var handle, and it says, well, if the var handle is operated on, so when you really then use the var handle, then the declaring class will be initialized if it has not already been initialized. So you would assume in this example here, it's like, well, I'm not operating on the var handle, so it's like, no, my holder class cannot be initialized. But it is, because find static var handle has the bug, and when creating the var handle, it actually triggers initialization. It's interesting that bug has been in the JDK since the beginning of var handles, which is, I think, Java 9. And finally, in JDK 22, it's getting fixed. There's like, apparently, no one except we, when building native images, really observed this strange behavior that, well, there's too early class initialization. But it is a problem, as I will tell you later on. You also need to be very careful with new Java features triggering class initialization. So it's like Java 21 is adding enum switches, and it's like where you can now have null values. And the way it's implemented is kind of with a bootstrap method that kind of does some internal lookups. And when that whole feature was merged and integrated first into JDK 21 and build 23, it's like, oops, you had class initialization of this enum, even though I'm never using the enum because I'm only doing the switch on null. And the class initialization happened, well, in this bootstrap method invoker for the enum switch method when running the bootstrap method. Then it was materializing all enum constants, which means, well, you needed to initialize the enum. After I pointed that out on the pull request that enabled the feature, it's like, well, maybe that's not a good idea. Luckily, it got fixed quickly. So it's like now in Java 21, that thing is fixed. But it comes at a cost. Because the cost is now, well, the bootstrap method, which is supposed to kind of do things to bootstrap this enum switch, actually cannot do most of its work because it can only generate one data structure that stores another resolved enum label object that then lazily materializes the enum. So it's like, yeah, you fix the class initialization problem, that's good, but it comes at the performance and footprint cost because like it comes at the cost of doing things lazily again and yeah, not being able to constant fold and do really everything you want at bootstrap method time. So the summary so far is cyclic dependencies are definitely a source of bugs and deadlocks. Class initializer often capture external state that is not really immutable. And this capturing happens at pretty random times. And that is a problem also, I just want to mention it from a point of view of security, of course, because like, well, class initializers, especially of JDK classes, are kind of trusted code. It's like, well, you're initializing a core JDK class, and without that, the JDK is not functioning properly. But it's triggered by untrusted user code. And as I already said, it's like if you're unlucky and you have a stack overflow, then you can actually pretty easily make a denials of service attack on your JVM by making core JDK classes unusable. It's like you just fill up your stack and catch the stack overflow error. And then when you know the stack is full, then you trigger class initialization and you have kind of ruined your VM. And it's like, as part of the GraalVM project, we're kind of working on a secure code sandbox where it's like, oh, we want to be able to really run untrusted code in the same process, in the same VM as trusted code. And that's something we needed to mitigate for. Like, we really needed to make sure that's like, oh, when you are about to initialize a class of the JDK, you need to make sure that you kind of have enough stack space available so that, well, most likely, you're not going to run out of stack memory and kind of have an attack surface here. And my argument is like, well, class initialization, well, the fact that class initialization is not happening at a certain point is, of course, not tested much in Java compatibility tests. Because like, it's also very tedious and difficult to test. Because like for every feature, for every kind of API method, you would need to really make a special test that says like, oh, if I invoke that thing with an uninitialized class, then after I invoke this method, the class is still not initialized. So it's like you would kind of, for every kind of little thing in every test, you would kind of need to make a copy and says like, yeah, now I try this thing with an uninitialized class. So it's like, it's very difficult to test. So arbitrary code runs at arbitrary times in arbitrary threads. That's the summary of class initialization. But it has always been that case. So it's like, we now have nearly 3 decades of class initialization in Java, and it's like, why is this a problem? Well, first, of course, it's like, it's never too late to improve and to fix long-standing problems. But the real reason why it comes up is like, it's push to improve application startups. And there are all of these snapshotting and startup improvements that have been proposed. And it's like, there's, of course, my day job, GraalVM native image. There's OpenJDK project Leiden. There's OpenJDK project Crack. And it's like, we want to kind of snapshot things at build time or once at startup time so that we don't need to do them over and over again. But for that, of course, we need to run initialization code. And to run any kind of initialization code, we really need to kind of have initialized classes. Otherwise, we cannot really run initialization code. And all the examples that I had before were kind of things that we really want to do only once and constant for. If I have an annotation lookup, and just by looking at it, I know the result of it. I know is annotation present is always false. It's like, I want to execute that at image build time in GraalVM native image. I want to write a condenser that kind of replaces this annotation lookup with false. But can I? It's like, it has the side effect of, it might trigger some sort of class initialization. So it's like, is that specified that I can do that and just ignore the class initialization side effect? And such say I return false and, well, the class remains uninitialized. Can I just run the class initializer and early on run arbitrary user code? That actually, we learned the hard way, you cannot do that. So it's like, if you're not 100% sure that a class initializer is side effect free, you can really not run it eagerly, because it's like every framework, every large application has some dark area where there are class initializers that would run and they have side effects, and that must not happen. So it's like, you really need to be very careful there. So how bad is the problem? As I said, I spent too much of my lifetime already kind of on a class initialization. So what we did for GraalVM native image is like, we decided like, well, we cannot just run class initializer. So we implemented a simulator for class initializer. That's a fancy way of saying, or symbolic execution. That's kind of fancy way is like using the partial evaluator that we already have for our truffle languages, and we run it on class initializers. And it's like, if the partial evaluator says it's like, yeah, everything that's in this class initializer kind of got partially evaluated away. It's like, oh, it's only allocating objects, it's only storing and loading from these objects, then all is good. And after simulation, kind of you end up with an empty class initializer because it was completely simulated. Then it's like, yeah, the class initializer is okay and does nothing bad. And then there are class initializers, of course, that cannot be simulated. And if they cannot be simulated, then we know all the reasons why. Because we know all the reasons why we aborted a simulation. So I looked at kind of the output of that for one large application. My go-to application is Spring Pet Clinic. So with Spring Boot 3, because first it works nicely on native image, and second, it's pretty large. It kind of has everything in it that you can imagine: Hibernate, JDBC drivers, JSON serialization, deserialization. So it has about every dependency you can imagine. So it's good enough to kind of be a large application to analyze. One thing I need to say is like, as part of GraalVM native images, like we kind of always force initializing a good number of the Java base module always eagerly. So it's like, this analysis does not cover kind of the core JDK classes, but it covers everything that kind of then is in the user code running on top of the JDK. So in total, there are 22,700 classes that get analyzed. First question is, well, how many classes do we even have class initializers? Actually, a good quarter of the classes have a class initializer. And then there is this super type problem. So it's like 3,000 classes, even though they don't have a class initializer themselves, they rely on a super type that has a class initializer. So from the point of view of class initialization, you need to treat them as if they have a class initializer. So nearly 9,000 of the classes actually need to be simulated. And most of them actually, or 2/3 of these classes with class initializers can be simulated, and about 3,000 classes are left that cannot be simulated. So it's like, you can say, well, not too bad. It's like you have a very large application and you have only 3,000 class initializers. Or you can take the class half empty look and say, it's like, well, 3,000 classes actually have class initializers and these class initializers are non-trivial and I really need to do something. So it's like, I would like this number to get much lower in the future. But now we can look at like, well, of these 3,000 classes, what are they actually doing? And the first thing is like, I looked kind of at the first reason why a class cannot be initialized. That's kind of an approximation of all reasons, because like, well, usually if the first thing that the class initializer is doing, you could say is like, yeah, that might be the most important thing now because it's the first thing. And the first thing for many classes is, of course, well, you go to the super type initialization or a cycle member. there's like more than a third of these class initializers actually are blocked because already a superclass has a problem, which is good and bad. Yeah, good thing is it's actually not so difficult to fix because it's like we just need to decouple class initializers more, and so it's like, well, if we kind of isolate the state that needs initialization into classes that don't have subclasses, kind of isolate these things more, then we actually can get away and remove a good number of dependencies immediately. So that's kind of solvable by reducing class dependencies. And then there is this big thing. Next thing is like more than 600 classes. The first thing they do is they allocate a logger in the class initializer. And it's like, there's not one kind of logging, of course, in every big application. It's Spring Pet Clinic, so it kind of is a mixture of many libraries and frameworks. So there's JBoss logging, there's Hibernate logging, there's Apache Commons logging, there's SLF4J logging, there's Java util logging, and you can look at all the different counts. But of course, it's like allocating a logger in a static final field is a very common pattern. It's a very convenient thing, but it's like, from a point of view of improving application startup, it's certainly not the best thing you can do in a class initializer. And the other thing is like, well, there are 54 classes that initialize and compile a regular expression in pattern. Also not great for your application startup. It's like you have a utility class that has lots of static utility methods, and most of them are pretty trivial methods, but it's like before you can use the first utility method, you need to compile a regex pattern, because it's like there is a static final field with a regex in this class too. It's like, that's definitely an area where lazy initialization can help. It's like, that's something we need to kind of shift to later, because it's like, well, you don't need to allocate the logger until you really need to log the first time. And it's like, just because you invoke one method or you allocate an instance of a class doesn't mean you really have something that's already loggable. And that's like shifting things to later would help here. Then there are kind of, you could say, valid uses of why a class cannot be simulated. System.getProperty might be in this case, if it's really a system property that is like something that the user wants to configure. There might be stupid system properties. It's like, if someone looks at the architecture or the CPU that you're running on, then it's like, that's probably something you could do eagerly too. But there are definitely a couple of things that you really should do eagerly. It's like, Spring Framework has this class utils.isPresent method. It's like, that's definitely something you want to fold to the build time, because it's like, well, if you already kind of have an application that you deployed, and it's like, I don't need to look in a class initializer if something is present. It's like, that's the prime example of like, I run it once at build time, and everything that is present kind of gets constant folded. And then there's this long list of funny things. The one thing I picked out is allocation of a thread local. Why would be the allocation of a thread local be a problem? It's like a thread local is just an arbitrary Java object. It's like, as long as you don't access it, it does really nothing. But it's one of these examples of kind of benign shared state, where it's like, if you look at thread local, it kind of computes the hash code of the thread local, which kind of has a global counter that it increments for every thread local, which means if you look at it with application knowledge, you can say it's like, yeah, you can run that eagerly, because it doesn't really, the order of class initialization doesn't matter. But it's like, it's nothing that can be really done automatically, because it's like, as soon as we see something, someone is writing to an atomic integer, it's like, we need to say, it's like, simulation stops. It's like, you're mutating a shared state. We cannot do that automatically. But it's like, we can kind of look at these things and kind of do manual eager initialization, and it's like, I know this is safe, even though it's mutating and accessing shared state. But with my domain knowledge, I can do that eagerly. For the fun of it, I also looked at kind of, how many classes actually do have static state. By static state, I mean kind of any kind of static field. And I really want to differentiate between mutable static state and immutable static state, because immutable static state is fine. It's like if you just, for example, have an enum that allocates enum objects, things that never change, it's like that's okay. If you have a class with mutable static state, you need to be careful, because it's like you cannot really just say it's like, you preserve the output of all static fields and kind of start your next execution with these static fields, because they might be mutable. And so it's like, it's half-half in terms of classes that have static fields. Half of them actually have mutable static state, but half don't have mutable static state. So that's actually pretty good news. And I really did a deep analysis. So it's like immutable static state really means that it's like, the class has a static field of some declared type, and that declared type only has final fields too. So it's like it's really a transitive kind of analysis. So, what can we do? As I said, the wild and crazy ideas, but actually looking back at my wild and crazy ideas, I have to say most of my wild and crazy ideas are actually ideas that probably people often come up with, but actually don't solve the problem. So it's like kind of as a starting point with non-starters. Removing class initialization altogether would be nice, but first it's not likely, and it doesn't solve any problem, because it's like, even if we today say all classes that we compile from now on don't have class initializer, we still have 30 years of history of classes with class initializer, and we need to be able to run them again. So it's like we cannot just reject them. And the prime example for that is like, the GSR red bytecode, which got removed in Java 5, I think, and all code compiled since then no longer has GSR red, but still every compiler, every tool that is out in the Java side needs to handle the bytecode, because it's like there's still enough code out that uses it. So it's like, class initializer kind of are here to stay. We can relax the specification and say it's like, class initializers already kind of run at arbitrary times. We can write it in the specification that this is allowed, but also not really a solution for any problem, because it's like, doesn't make programs more correct just because it's like you tell people that their class initializer runs at an arbitrary time. So it's like, we need to tell people how to fix the problem and not kind of make it legitimate to kind of make the problem worse. One thing that we kind of settled on in GraalVM native image is that we kind of have a flag on classes marking them explicitly as eager initialize. And in GraalVM native image terminology, it's called initialize at build time. And that, the good news of that is it's like, it works because it's like we're using it in production. The bad news is it's very easy to make mistakes. Because like, you can mark a class as eagerly initialized, and that class does a system out print line, and we just need to trust the programmer and the user to say that they know what they are doing. And as we know, it's like people in this room know what they are doing, but it's like arbitrary Java developer often just don't do it. It's like, how do I fix my problem? I mark the class as initialize at build time, and so I do it. So it's like, it's something that we can consider, but it's definitely not the best solution. There have been all these proposals of kind of separating initialization for static fields. It definitely makes things better. So it's like if you can mark a static final field as lazy, and it's like, this initialization of this field only runs when the field is accessed. Or he recently proposed computed constant. Definitely makes things better for things in this category that I showed. Is kind of, I'm initializing a logger, I'm kind of initializing a regex pattern, because it's like these things you can really kind of do lazily. But it fundamentally does not solve the problem of class initialization. Because it's like, I still have this computed constant in the static final field. And if I have a computed constant that wants to reference another computed constant, that comes from a static final field of some other class. So it's like the only thing you're doing with lazy static final fields is like you make it lazy, so things happen later, but there's no way with this mechanism to actually make things happen earlier. So it's like you cannot kind of have these lazy fields kind of be initialized early without kind of leading to the same problems as initializing the whole class eagerly early. So again, it's like improvement of some things, but does not solve the real underlying problem. The best thing I so far could envision is kind of another kind of flag for classes. So it's like that I as a programmer can really say, oh, I have an opt-in, my class does not do any bad things in class initializers, and then the compiler really checks that. So it's like really make it an error to say it's like, oh, I have mutable static state, and really make it an error saying I'm having a class initializer with side effects. From a point of view of native image and Leiden and kind of snapshotting, I think that's a very promising direction because it really means that it's like, oh, if someone wants a class to be kind of usable in these early stages, and then this class is clearly marked and things are safe and things are guaranteed. We can discuss lots of different definitions of what is snapshotable, what is no longer snapshotable. I don't want to go into details here. It's like, of course, you need to make it broad enough so that enough classes can be snapshotable, but it's like narrow enough so that you don't run into class initialization problems. But the real thing, I think, for users is like we kind of just need to tell them when they screw up in their class initializer. So it's like we kind of need to help maybe in Java C with a warning or in the IDE with kind of making it easy and to people to just click around their source code and say, it's like, oops, if I'm to initialize this class, I actually need to initialize all of these other classes. Or the IDE can tell me, well, this class is not snapshotable because it's like I have this one static final field, and if you move this one static final field kind of into its own class or into a kind of a lazy field, then suddenly so many more classes would kind of be class initializer free. There's like, I think there's a lot we can do there. And on the GraalVM native image side, we are kind of very early in that because now we have this simulation of class initializer. So at least we have kind of a good list of reasons of what people could do to improve their class initializers. And with this reason list of why a class initializer cannot be simulated, it's like we can tell users like, yeah, now if you fix this thing, then this class can be simulated and your class initializer is overall kind of better. So to continue on my summary, yes, class initialization is a problem, and it's a major blocker. And I think one, actually on the native image side, the biggest kind of complication and blocker that really kind of makes it difficult to use for users. But it's a real challenge to find a solution. So it's like, I think we need to kind of spend more time on kind of thinking about solutions and kind of coming up with how do we make it easy for people to use a class initializer kind of to get what they want in terms of kind of initializing immutable static states, but kind of preventing them from making common mistakes. And that's all that I had. Thank you very much.